Hi, this is the second lesson of topic 13 on electromagnetic induction. And this lesson follows on from the first where we learnt about generators. Let's have a quick recap. You hopefully remember the motor effect. The motor effect governs how motors work, where electrical energy, like from this battery, is converted into kinetic and mechanical energy. Electromagnetic induction, on the other hand, is used in generators, where mechanical and kinetic energy is converted into electrical energy. So for example, the mechanical and kinetic energy of the hamster running on the wheel is converted into electrical energy in this phone. It's similar when we look at this diagram and here as well. For this lesson, the other thing we need to recall is Fleming's left-hand rule. First, form your hand into the shape shown on the screen. The thumb represents the motion of our current carrying wire. Our first finger shows the direction of the magnetic field, and the second finger shows us the direction of the current. Now let's take a look at a diagram showing a generator. Now there are two types of generators, alternators and dynamos, but we'll come to this distinction in a bit. Take a look at this diagram. Based on the direction of motion of the coil, think to yourself, in which direction is current induced? Use Fleming's left-hand rule to figure it out. Pause the video and have a go. So, let's deal with the left-hand side first. The coil moving in the upward direction. Our thumb represents the motion in the upward direction. Our finger represents the direction of the field. And our second finger represents the direction of the current flow. So our current flow is in this direction. Let's try it for the other side. In this case, our thumb will be pointing downwards because this is the motion of the coil. Our field will still point to the right, as is the direction of the magnetic field, and our current will be in this direction. This is the position of maximum potential difference. This is the position where the most current is induced, and this is because our coil is cutting the magnetic field lines directly. The key thing to remember is that current first flows through slip ring B and then to slip ring A. So from B and to A. It's really important to remember when distinguishing between an alternator and a dynamo. So first from B and then to A. Make sure you remember that. What about this situation here? Do you think this point will induce a maximum potential difference or no potential difference at all? Pause the video and think. Based on what we said earlier and the language I used, at this point, the coil is not cutting the magnetic field lines. Therefore, no potential difference is induced. Now let's take a look at this diagram again. It's very similar to the one before, but now we have yellow on this side and green on this side. What happens in this situation? Pause the video and think. So your instinct should have been to use Fleming's left-hand rule. Because the wires of the coil are directly attached to slip ring A and slip bring B respectively, the direction of current now changes. This time it's going through A and to B. So it starts at A and then goes to B. This has changed the direction of current flow. This switch can also be shown on a diagram. Now, as the coil continues to rotate, which graph, A, B, or C, do you think represents the current being induced? Pause the video and think. So, as mentioned earlier, potential difference will continue to alternate in direction. It'll go from the positive end to the negative end, from the positive side to the negative side, and this will continue. So, this is characteristic of alternating current, and thus alternators generate an alternating current. This is what's shown in diagram A. The maximum occurs when the wire is moving perpendicular to the magnetic field, and the minimum occurs when the wire is moving parallel to the magnetic field. And once again, the negative maximum occurs when the wire is again perpendicular to the magnetic field, but it's now just moving in the opposite direction, just like we saw before. And this cycle repeats. This is the first type of generator. This is an alternator. This diagram is for a dynamo. It's very similar, but with one key difference. A dynamo has one split ring commutator. The alternator had two rings, but a dynamo has one single ring. Everything else remains pretty similar. These diagrams show the three phases of a dynamo. In the first phase, using Fleming's left-hand rule, we're able to deduce that the direction of current is in this direction, very similar to an alternator. Next, as our coil rotates, again, like our alternator, the dynamo induces no current in this phase. And that's because our coil is not cutting the magnetic field lines. It's moving parallel to the magnetic field lines, as shown here. We can see that due to the split ring commutator, which rotates as the coil rotates, current still flows out of side B and in to side A. This is very similar to what we see in phase 1. The direction of our current flow hasn't switched because our commutator has rotated and switched direction. So current still flows out of side B, just like in phase 1, and in to side A, just like in phase 1. This is a key difference between an alternator and a dynamo. So as we can see, our start position and end position are very similar. In fact, the current and potential difference does not reverse in a dynamo. As the current flow doesn't reverse, dynamos produce direct current. So, which of these diagrams do you think represents a dynamo? Is it A, B, C, or D? Pause the video and have a go. As you know, dynamos only induce current in one direction. Therefore, diagram B is our answer, because current is only induced in the positive direction and doesn't flow in the negative direction, unlike the other diagrams. This diagram is largely similar to the first one we saw. The maximum occurs when the wire is moving perpendicular to the magnetic field and directly cutting through it. No current and no potential difference is induced when the wire is moving parallel to the magnetic field, as again the magnetic field lines are not being cut. And this process repeats itself. It's really important to note, for every full 360-degree rotation, we have two peaks. That's because for one rotation, our alternator diagram would look like this. But our dynamo diagram looks like this. That's it for this lesson. I hope you found it useful. If you have any questions, please do ask.